What if one wrong calculation could destroy a 12 kilowatt inverter in the middle of winter? In today's video, I'll show you exactly how to design a powerful solar system the safe way, even in extreme temperatures. Welcome back to AK Electric DIY, the channel where we break down real-world solar, electrical, and energy systems, step by step, without the guesswork. This video is based on a subscriber request from Mihai in Romania, who asked for a complete tutorial on setting up a 12 kilowatt all-in-one hybrid inverter paired with a 20 kilowatt hour battery using 580 watt solar panels. We'll cover how many panels you can safely connect, how MPPT limits really work, why cold weather is more dangerous than heat for solar voltage, and how to oversize your PV array without destroying your inverter. This tutorial is designed for DIY solar builders, professional installers, and engineers who want numbers that actually make sense, not just theory. So if you're planning a high-power solar system, or you live in a climate with freezing winters and hot summers, make sure you watch this all the way through, because one small mistake here can cost thousands. Before we connect a single solar panel, we must clearly understand what this inverter can and cannot handle. The heart of this system is a 12 kilowatt all-in-one hybrid inverter. That means the maximum AC output power is 12,000 watts, no matter how many solar panels you connect. This inverter has two independent MPPTs, and each MPPT can handle up to 6 kilowatts of solar input. That's important because each MPPT tracks its own string of panels, and they must stay within very strict electrical limits. The maximum PV voltage allowed on this inverter is 500 volts. Go above this, even for a moment on a cold winter morning, and you risk permanent inverter damage. The maximum PV current per MPPT is 27 amps. Exceeding this won't usually destroy the inverter instantly, but it forces the MPPT to clamp or shut down, wasting power and stressing internal components. The inverter's PV operating voltage window is 120 to 500 volts. Your solar strings must stay inside this range during all seasons, from summer heat to winter frost. Inside this unit is also a 20 kilowatt hour integrated battery, which stores excess solar energy and supplies power when the sun is gone. And this is why inverter limits matter so much. You can safely oversize solar power, but you can never oversize voltage. Understanding these limits is the difference between a reliable solar system and an expensive mistake. Now let's take a closer look at the solar panels, because this is where most system design mistakes begin. The panels used in this system are rated at 580 watts each. That's a high-power modern panel, commonly used in residential and small commercial installations. But wattage alone is not enough information to design a safe solar system. The first critical number is VOC, or open circuit voltage. For these panels, the VOC is 51.3 volts. This is the maximum voltage a panel can produce when it's not connected to a load, and this is the number that can kill an inverter if ignored. Next is VMP, or voltage at maximum power. For these panels, VMP is 43.3 volts. This is the voltage where the panel actually operates most of the time when producing power. Now, here's the most important and most misunderstood specification, the temperature coefficient of VOC. For these panels, the temperature coefficient is minus 0.26% per degree Celsius. What this means is simple. As temperature drops, voltage increases. On a cold winter morning, solar panels can produce much higher voltage than their rated value, even if the sun isn't very strong. This is why VOC and temperature coefficient matter far more than panel wattage when designing strings. Ignore this, and your system may work perfectly in summer, but fail catastrophically in winter. In the next section, we'll calculate exactly how cold weather affects these panels, and how many you can safely connect in series. To design a safe solar system, we must design for the worst weather, not the average day. This system is located in Romania, where winter temperatures can drop to -20 degrees Celsius and summer temperatures can rise to +50 degrees Celsius. These extremes have a direct impact on solar panel voltage. When it's cold, solar panels produce higher voltage. This is when inverters are most at risk. When it's hot, solar panel voltage drops, even though the panels may still produce high power. So remember this simple rule. Cold weather increases voltage, hot weather decreases voltage. That's why all solar string calculations must be based on the coldest expected temperature, not summer conditions. In the next section, we'll calculate exactly how much the voltage increases at -20 degrees and how many panels we can safely connect in series.
This is the most critical calculation in the entire solar system design. We calculate worst-case cold VOC because overvoltage happens silently, and once it happens, the inverter is already damaged. Solar panels don't fail in winter because of snow. They fail because cold increases voltage. Every solar panel voltage rating is measured at a reference temperature of 25 degrees Celsius. But in Romania, winter temperatures can drop to -20 degrees Celsius. So first, we calculate the temperature difference. 25 minus -20 gives us a difference of 45 degrees Celsius. Now we apply the temperature coefficient of VOC, which for this panel is -0.26% per degree Celsius. We multiply 0.26% times 45 degrees. This tells us the total voltage increase percentage. That equals about 11.7%. Now we apply that increase to the panel's rated VOC. The rated VOC is 51.3 volts. 51.3 volts multiplied by 1.117 gives us a new cold weather VOC of about 57 volts per panel. Now we ask the most important question. How many panels can we connect in series without exceeding the inverter's 500-volt limit? 500 volts divided by 57 volts gives us 8.7 panels. Since we can't install a fraction of a panel, we must round down. That means the maximum safe number is 8 panels per string. If you install 9 panels in series, the system may work in summer, but on a cold winter morning, the voltage can exceed 500 volts and permanently destroy the inverter. This is why voltage limits are never negotiable.
Now that we've done the cold weather calculations, we can confidently design the solar string configuration. From the previous section, we know the maximum safe number of panels per string is 8. Let's verify this design by checking both voltage extremes. First, cold weather open circuit voltage. At -20 degrees Celsius, each panel produces about 57 volts. With 8 panels in series, the total string voltage is 8 multiplied by 57, which equals approximately 456 volts. That stays below the inverter's 500-volt maximum limit, so the system is safe in winter. Now let's check normal operating voltage, also called VMP. Each panel has a VMP of 43.3 volts. 8 panels in series gives us 8 multiplied by 43.3, which equals about 346 volts. This value sits comfortably inside the inverter's MPPT operating range of 120 to 500 volts. That means the inverter can track power efficiently and operate without stress. So, to summarize, cold weather VOC safely below 500 volts, operating VMP well inside the MPPT range. This confirms that 8 panels per string is the correct and safe configuration for this system. In the next section, we'll connect these strings to the inverter's MPPTs and calculate the total system power. Now that we've confirmed our string voltage is safe, let's design the MPPT layout with actual panel specifications. Each 580-watt panel has open circuit voltage of 52 volts, short circuit current of 13.7 amps, and max power current of 13 amps.
For safety, we always use short circuit current for MPPT calculations. Let's calculate one string first. 8 panels times 580 watts equals 4,640 watts, or 4.64 kilowatts. Current check for parallel strings. 2 strings in parallel means double the short circuit current. 13.7 amps times 2 equals 27.4 amps total. Our MPPT limit is 27 amps, so we're slightly over the limit. In practice, panels rarely hit their maximum short circuit current, and most inverters have a small safety buffer. But to be absolutely safe, we have 2 options. Option 1, use 1 string per MPPT, 16 panels total. Option 2, choose a different panel with lower current or an inverter with higher MPPT current rating. For this example, we'll proceed with 2 parallel strings, but I strongly recommend verifying with your specific inverter manufacturer if 27.4 amps is acceptable on a 27 amp MPPT. Voltage check recap. 8 panels at 52 volts equals 416 volts. After cold temperature adjustment, about 460 volts. This must be below your inverter's maximum PV input voltage. With 2 MPPTs each handling 2 strings, we have 4 strings total, 32 panels, and total array size is 18.56 kilowatts. The inverter's 12 kilowatt AC rating gives us a 155% oversizing ratio, which is optimal for energy harvest, especially with battery storage. Design corrected summary. Parameter calculation, MPPT limit, status. Current per MPPT is 2 times 13.7 amps equals 27.4 amps. The MPPT limit is 27 amps, and we have a caution sign. It exceeds by 0.4 amps. Voltage per string is 8 panels times 52 volts equals 416 volts, plus cold temperature. The typical limit is 450 to 600 volts, and this is likely okay. Power per MPPT is 2 times 4.64 kilowatts equals 9.28 kilowatts. The MPPT limit is 6 kilowatts, and this is oversized, and we must check allowed buffer. Total system is 32 panels times 580 watts equals 18.56 kilowatts. The AC limit is 12 kilowatts, and this is intentional oversizing. Recommended solutions. Option A, safest. Reduce to 1 string per MPPT. 2 MPPTs times 1 string equals 16 panels total. Total power is 9.28 kilowatts. Current is 13.7 amps per MPPT, which is safe. Still provides 77% DC to AC ratio. Option B, verify inverter buffer. Some inverters allow 10 to 15% overcurrent temporarily. Check Donice specifications for max ICS or overcurrent tolerance. If manufacturer approves, proceed with caution. Option C, different panel selection. Choose 580 watt panel with ICS less than 13.5 amps, or select 550 watt panels with lower current. Key safety. Always use the panel's short circuit current, ICS, for MPPT calculations, not the max power current, IMP. The ICS is what flows during a fault or startup, and exceeding the MPPT's current rating can cause immediate protection trips or permanent damage. Action items before installation. 1. Verify exact panel specs from manufacturer datasheet. 2. Contact Donice to confirm if 27.4 amps on a 27 amp MPPT is acceptable. 3. Calculate exact cold temperature voltage for your location. 4. Consider safety margin. 27.4 amps is at 101.5% of rating, no margin.
Now, here's the part that confuses and scares a lot of people. PV oversizing. How can you connect more solar power than your inverter rating without blowing it up? Let me show you how oversizing works, what is safe, and what is absolutely not. Oversizing your solar array is actually a good thing when done correctly. It helps you produce more energy in the morning, in the evening, during winter, and on cloudy days. With batteries, it also means faster charging and less grid dependence. What oversizing does not do. Here's the most important thing to understand. Oversizing does not increase your inverter output power. A 12 kilowatt inverter will always stay a 12 kilowatt inverter, no matter how many panels you connect. How MPPT current limiting protects the inverter. Modern hybrid inverters protect themselves using MPPT current limiting. When the solar array can produce more power than the inverter can accept, the MPPT simply limits the current. The extra power is not used and nothing gets damaged. But here's the critical warning. Voltage is different. If you exceed the inverter's maximum PV voltage even for a moment, there is no limiting, no protection, and no second chance. Safe oversizing range explained. For most modern hybrid inverters, a safe PV oversizing range is typically between 120% and 160% of the inverter's AC rating, as long as voltage and current limits are respected. This is why we calculate cold weather voltage and MPPT current so carefully. So remember this rule. Power can be oversized, current can be limited, voltage must never be exceeded. That's the difference between a smart system and a dead inverter.
You can design the perfect solar system on paper, but bad wiring can still cause power loss, overheating, or even fire. So now let's talk about DC wiring and cable sizing and how to do it safely. DC string wiring basics. Each solar string is wired in series to increase voltage. When strings are combined in parallel, the voltage stays the same, but the current increases. This is why cable sizing is based mainly on current, not power. Cable size short runs. For short runs, typically under 10 to 15 meters, 6 mm squared solar DC cable is usually sufficient for one string. It safely handles high DC voltage and keeps voltage drop low. Cable size long runs. For longer runs, especially over 20 meters, you should upgrade to 10 mm squared cable. Thicker cable reduces voltage drop, improves efficiency, and runs cooler. Importance of quality MC4 connectors. Never underestimate your connectors. Always use genuine MC4 connectors, properly crimped with the correct tool. Cheap or mismatched connectors are one of the most common causes of DC fires. Avoiding voltage drop final tips. As a general rule, aim to keep DC voltage drop below 2 to 3%. Shorter cables, thicker conductors, and solid connections all help. Good wiring doesn't just improve efficiency, it protects your system for years. This is the most important section of the entire system. Solar systems don't usually fail because of panels or inverters. They fail because of missing protection. Safety devices are not optional. They protect your equipment, your home, and your life. DC side protection, PV plus battery. DC isolators, PV side. Every solar system must have a DC isolator between the panels and the inverter. This allows you to safely disconnect the PV array for maintenance or emergencies. String fuses. Because we're using parallel strings, string fuses are mandatory. Each string must be protected individually to prevent reverse current during a fault. DC surge protection device, Type 2 SPD. DC surge protection protects your inverter from lightning-induced voltage spikes, even indirect ones. For rooftop systems, Type 2 DC SPD is the minimum requirement. Battery DC breaker, 20 kilowatt-hour battery. Your battery bank needs its own DC circuit breaker.
For a 20 kilowatt-hour battery on a 12 kilowatt inverter, use a properly rated breaker capable of handling high DC current. AC side protection. AC isolator and main AC circuit breaker. On the AC side, an AC isolator allows safe inverter shutdown. A main AC circuit breaker protects against overloads and short circuits. Under-over voltage relay. An under and over voltage relay protects your appliances from unstable grid or generator power. If voltage goes outside safe limits, it disconnects instantly. AC surge protection. AC surge protection is just as important as DC. A Type 2 AC SPD protects your inverter and home from grid-side surges. Load breakers and ATS. Each major load circuit should have its own breaker, and if you use grid and generator input, an automatic transfer switch ensures safe and seamless switching. Grounding/earthing. Grounding requirements. Grounding ties everything together. Panels, inverter, battery, SPDs, and AC distribution must all be bonded to a common earth system. Why safety devices are mandatory. Safety devices don't make power, but they prevent disasters. Skipping protection might save money today, but it can cost you everything tomorrow. Let's now connect the entire 12 kilowatt solar system step by step, starting from the solar panels and ending at the house loads. I'll explain this in a simple way, so even beginners can follow the full wiring logic safely. First, we start with the solar panels on the roof. Each solar string is made by connecting 8 580-watt panels in series. When panels are connected in series, the voltage increases, but the current stays the same. We make 2 identical strings like this. These 2 strings are then connected in parallel so the voltage stays the same, but the current increases. This parallel connection is done using a string combiner or MC4Y connectors, depending on the system design. Before the solar power enters the inverter, each string must pass through a DC fuse. These fuses protect the system if one string develops a fault and tries to send current backward into another string. After the DC fuses, the cables go into a DC isolator. This isolator allows us to completely shut off solar power for maintenance or emergencies. From the DC isolator, the cables then pass through a DC surge protection device, also called a DC SPD. This protects the inverter from lightning and voltage spikes. Now, the solar DC cables are connected to the PV input terminals of the inverter, matching the correct polarity, positive to positive and negative to negative. Each MPPT input receives its own pair of solar cables. Next, we connect the battery to the inverter. The battery positive cable goes through a DC circuit breaker and then into the inverter's battery positive terminal. The battery negative cable connects directly to the inverter's battery negative terminal. This DC breaker allows safe isolation of the battery and protects against overcurrent. Now we move to the AC side of the system. Grid power first enters a bidirectional energy meter. This meter measures how much electricity is imported from the grid and how much is exported back. From the meter, the AC power passes through an AC isolator switch. This allows the inverter to be safely disconnected from the grid. After the AC isolator, the power flows through an undervoltage and overvoltage protection relay. If the grid voltage becomes too high or too low, this relay disconnects the inverter automatically. Next, the AC cables pass through an AC surge protection device. This protects the inverter and household equipment from grid-side voltage surges. From the surge protector, the cables go into an AC circuit breaker rated for the inverter output. This breaker protects the inverter from overloads and short circuits. Now the inverter's AC output is connected to the load distribution board. Each group of loads, such as lights or sockets, is protected by its own load circuit breaker. If the system includes grid and backup power sources, an automatic transfer switch, or ATS, is installed. The ATS safely switches the power source between grid, inverter, or generator without any backfeeding. Finally, we connect the earthing system, the solar panel's frames, inverter body, battery casing, DC SPD, AC SPD, and distribution board are all connected to a common earth point. This earth connection safely directs fault current and lightning energy into the ground. When all these connections are done correctly, the system operates safely, efficiently, and reliably. Every wire has a purpose, and every protection device prevents damage before it happens. This is how a complete 12-kilowatt solar power system is wired, step by step, the correct and safe way.
Before we finish, let's quickly talk about some of the most common mistakes people make when designing or installing solar systems. The first mistake is connecting too many panels in series. This can push the solar voltage beyond the inverter's limit, especially in cold weather, and that can permanently damage the inverter. The second mistake is ignoring cold temperature voltage calculations. Solar panels produce higher voltage when it's cold, not when it's hot. If you don't calculate cold weather VOC, your system might look safe on paper but fail in winter. Another very common mistake is not installing a DC isolator. Without a DC isolator, you cannot safely shut down the solar array for maintenance or emergencies. Skipping surge protection is also dangerous. Lightning and grid surges don't need a direct strike to cause damage. Without DC and AC surge protection, your inverter and electronics are exposed. Another mistake is mixing different panel orientations or tilt angles on the same MPPT. For example, east-facing and south-facing panels should never be connected to the same MPPT because they produce power differently and reduce overall system performance. Avoiding these mistakes can save you money, prevent equipment damage, and keep your system safe. Let's quickly recap what we covered in this video. We explained how to safely design a 12-kilowatt solar system, how to calculate panel voltage and current, how to configure strings and MPPTs, how to size cables, and why protection devices and grounding are critical. A big thank you to Mihai from Romania for asking this question and inspiring this detailed tutorial. If you found this video helpful, please like the video, subscribe to AK Electric DIY, and share it with anyone planning a solar installation. And if you have a different inverter model, leave a comment below with your inverter specifications, panel type, and location, and I'll try to help you design a safe system. Thanks for watching, stay safe, and I'll see you in the next video.